Okay, so today we will look at kind of Bayesian statistics in for linear regression. Okay, so in Bayesian statistics, we said we think of the parameters as random values, and the parameters themselves must come from some probability distribution, right? So so if we're thinking about linear regression, what are the parameters of our model? The parameters are the intercept and the slope, right? So we will call the intercept W0 and the slope W1. And the idea here is that these parameters themselves come from a probability distribution. So W0 and W1 come from some probability distribution. Okay. And if we think about the intercept and the slope, are these two things independent, or is there some kind of relationship between them? There's some kind of relationship, right? We saw that, you know, in previous examples, we saw that if the slope increases and gets more steep, then the intercept will tend to decrease, and if the slope goes the other way, then the intercept will tend to increase. So they are not independent, and so when we say some probability distribution, this is going to be a joint or a multivariate distribution. So, so we will have so our prior distribution on the parameters we're gonna throw both parameters into a vector W. Okay, so the prior distribution on the parameters in W will be just the probability of W, okay? And we might define this with some kind of what we call hyperparameters, okay? So these are coming from some kind of distribution, and so so this distribution can be any joint distribution over W0 and W1, okay? So the entire span of W0 and W1, this prior distribution can be anything, all right? The distribution that has nice properties, which we will call the conjugate prior distribution for linear regression, is going to be the multivariate normal or multivariate Gaussian distribution. Okay, so PW could technically be any distribution, really. Okay, but we will use the conjugate prior because of its nice properties. And so the conjugate prior is a multivariate Gaussian, or multivariate normal distribution, okay? And so a multivariate Gaussian has two parameters, which is going to be your mu0 vector and your sigma matrix, okay? And to assign these, to say that they belong to the prior distribution, we'll call them mu sub 0 and sigma 0. Okay, And so we will say W comes from multivariate normal with vector mu 0 for the mean and matrix sigma 0 for the variance. And or we can also just write, this is the probability of W given the hyperparameters sigma 0 and such. Okay, so these things define the prior distribution for W. Okay, so our intercept and our slope are random variables drawn from some distribution, okay, that considers all possible slopes and variances, okay? And then what we want to do is we want to look at our data and update our distribution, our beliefs about W based on what we see in the data. And so following Bayes' rule, okay, what we want is we want the posterior, which is going to be the probability of our vector W given the data, okay? I guess we'll have our data matrix X and our responses T, okay? And this will be proportional to basically the likelihood times the prior. So the likelihood is the probability of X given W times our prior, which is, I guess this is X and T, multiplied by the prior on W. Okay. There's actually another thing that comes in here. All right. So this likelihood, so again, if we think about our linear regression model, right, we've got some line. This is going to be W0 plus W1 X, okay? And for some X of I, this dot right here represents our Y hat, which is going to be W0 plus W1 X of I. And then we have to kind of pretend that there's some distribution centered here, and we might observe our actual Y to be right here. All right. And so this here, if we're assuming if our model says the errors are normally distributed, this is going to be the normal distribution. Okay, with mean equal to basically X, I'm going to just in matrix form, X times W, and basically error standard deviation equal to, we'll call this, we'll say sigma squared, okay? So the likelihood actually depends also on a sigma squared term. Huh? Yeah, the variance. All right, I'm sorry, what's that? Oh, error variance, sorry. Error variance sigma squared. Yes, thank you. Okay, so this is technically what is the probability so basically what is the likelihood of our data. No, I messed this up here. There's no x in here, the likelihood. The x is actually treated as fixed values. So the x goes back here, I apologize. Okay, so what is the likelihood of our data, basically our data responses, given x, sigma squared, and w? Okay, so this is going to be the probability of t given w, x, sigma squared. Okay, and then our prior distribution is the probability of w given our hyperparameters mu0 and sigma 0. Okay, and this is what we are going for, that our posterior distribution w given our x and our t and our sigma squared and the hyperparameters. So given everything else, it's proportional to the likelihood of our data multiplied by our prior. And what we have to do is we have to consider all the possible values of our slope and intercept in W. Okay, let me see if I can kind of illustrate what we're going to do. All right, so I will show you with grid approximation first, and then when the grid approximation breaks down, we'll do some math. So imagine this is, I've got my parameter space for W0 and W1. Okay, and so this considers all possible W0, W1. So technically, our W0 and our W1 could be, you know, anything from negative infinity to positive infinity, right? What we're going to do is we're going to look at the Olympic men's 100-meter gold medal time data. Okay, and so so here, where does this? So technically, we should create our priors before looking at our data, but we'll just take a peek at our data and take a look. Okay, so my here X is basically the Olympic event that was held. The very first one was 1896, and then 1900, and we kind of scaled them by 4. So then this is kind of what we see, and so. I guess the latest one was Olympics 29 or something, so that's like the 2012, I don't know, something Olympics a few years ago, right? 2008, I don't know. And then in our Olympic time, so we're just trying to fit a linear model here, right? And so here it looks like the intercept's going to be somewhere around 11 and a half, something around there if I had to guess. And it looks like our slope is that, you know, every 10 years it seems to drop maybe half a second, or not every 10 years, every 10 Olympics events, something. So our slope's going to be quite small. But anyway, we don't need to worry too much about that. All we have to do is basically, we could have a completely flat prior. Oops, that's not what I wanted. A completely flat prior would be any value from negative infinity to positive infinity is allowed, okay? but that's probably like way too general, right? Probably the intercept could be anything from 0 to 20 or something, 0 to 30, and we could even be just more generous, and we can just say we will consider for the prior we'll say the mean for the intercept. Mean intercept will be 0, but we will have a variance term of 100, okay? So that basically means 99.7% of values will be covered between -30 to +30, right? From our, what's that called? Empirical rule? All right, so this is gonna cover kind of all of our values, and then as far as the slope, we can have anything. What did I end up using? Okay, so I said from -6 to 6. So the slope is 0, and the variance is going to be actually, I think, 5. So yeah, so basically -6 to 6, square root of 5 is a little bit more than 2. But so this is just very, 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 it's much bigger than it needs to be, right? Okay, and then and we will just start off with kind of no covariance, because we have no idea really what it's going to be. So we're going to just start off with this very broad thing, and the way so this is the contour plot, but when I plot it in R, we're not seeking out the function. Basically, the way that R works is I'm going to just create a bunch of points. I'm going to say, all right, what is, if I plug this into, I've got in R, there's the multivariate normal function, and I ask what's the density of the multivariate normal at value, basically I'm going to put in the coordinate -36 if the mean is equal to 0, 0, and the sigma is equal to the matrix 100, 0, 0, 5. Sorry. Okay, and then I just say, okay, that's going to give me a value at this coordinate location, and I just go across and I calculate the values at all of these different coordinate locations. All right, so I'm going to get a grid, and I just fill out basically a matrix full of all of these things. Okay, so I'm not actually plotting the true function. I'm just saying, give me a bunch of, calculate a grid of points, and I'm going to just kind of assume smoothness in between, right? And that's good enough, okay? And so when I do that, okay, so the true answer is going to have an intercept of 11.13 and a slope of -0.05. Okay, so here's my prior distribution. I'm going to say, okay, my sigma is a diagonal matrix with 105 down the diagonal. Okay, and here we're going to make a grid going from -20 to 20 by steps of 1/2 unit. And we're going to go from -6 to 6 by steps of 0.1. I'm going to create a matrix that just, however long this is and this is, I'm going to just have that many coordinates in Z. And then every location on Z, I just have to go through every single row and every single column. I'm going to take the coordinates x1 sub I and x2 sub j. So it's going to start off at 6, -30, and then it'll go to 5.5, -30, 5, -30, so on and so forth, and do this. The computer will do it very quickly, and I'm going to say, what is the, DMV norm, density of the multivariate normal for that value at sigma equal to sigma, okay? And then we're going to create a perspective plot, which creates this nice little, hill, and then we can create a contour plot, and it looks like this. Is this okay? So this is, and in fact, if you install Perspective 3D GL, you can have a nice little, oops. All right, let me run this, run, and okay, let's run this now. Did I not load the library yet? No. Okay. I haven't posted this file online yet because it needs a lot of plot 3D GL. Sorry, I gotta load this library up. Maybe this is not as exciting as I think it is, but I think it's exciting. All right, and you can so you get this 3D plot, right? So we get, here's our contours, and then okay, so this is what the prior distribution looks like. Basically, the prior distribution says right now an intercept of 0 and a slope of 0 is most likely, but really anything, an intercept as high as 20 and a slope as strong as -4 is like still possible, okay? Which is like completely ridiculous to think about, but that's what our prior distribution says. It says like anything here is kind of good, right? This is better, I think, yes, the creation of the prior distribution can feel a tiny bit arbitrary, but it's better than just saying I have no idea, because no idea means -infinity to +infinity is okay, and that's certainly we can do better than -infinity to +infinity. Okay. Generally, if you're not confident about whatever you're looking for, you create your prior distribution with really large sigma variance values, okay, and then it comes through. Okay, so let's say we observe one data point, okay? So when we look at our Olympic data, there's actually only 28 Olympics that we are looking at, and or I guess 29, and our first data point, 1896, the finish time was 12. Okay, and so we're gonna start off, and we're gonna say the error term in the linear regression model, because we said t is basically equal to w0 plus w1x plus some error term, okay? And so here we've got 12 is equal to w0 plus w1, and x here is 0 plus some error term. And here we're going to say the error terms come from a normal distribution with mean 0 and variance sigma squared, and we are saying sigma is going to be equal, sigma squared is equal to 2, so sigma is equal to the square root of 2. This is what we are saying. This is a bit of an arbitrary value, okay, but it's okay. So so we throw that in there. We say s is the square root of 2, okay, and then I'm going to just create a basic x and t matrix, or just so t is just the value 12. And x is, I'm taking the intercept term because you have a column of 1s and then your actual x value. So I've got 1 and 0. Oh, I'm sorry, they're cut off on the screen. Okay, so x is 1 and 0 for the intercept. And then here we'll just to demonstrate kind of what we will be doing is I say, okay, if my intercept is 0 and my slope is 0, then what is the predicted value? My y hat, my mean is 0, right? That makes sense. That's just x times w in matrix notation. And then I would say, okay, what is the normal density of getting 12 if my mean is 0 and my standard deviation is the square root of 2, okay? And it says, all right, that is on the order of 0, okay? okay? And meanwhile, we can say, well, what's the prior probability of getting the coordinates 0, 0 for the slope and intercept from the prior distribution? And it says, well, that happens with probability 0.007 or something like that, okay? Okay, so what I'm going to do here is we're going to create a posterior distribution. And again, we're going to just approximate it using the grid. And here I'll just start going from, I forget, negative 20 to positive 20, okay? And we just create a grid from -6 to 6. Okay, and we'll put this thing here, okay? So at this coordinate, this represents W0 equal to -20 and W1 equal to positive 6. Okay. And, okay, so if the intercept is -20 and the slope is 6, then my y hat for the coordinate -20, 6 would be equal to -20 plus 6 times 0. My x is 0, right? Okay, and so my y hat is equal to -20. And then we say, okay, what is the t that we observed? Our t was 12, right? And we say, okay, what is, if the mean is -20, what's the probability I end up at 12? This is the likelihood of getting 12 if the mean equals -20 and I guess the standard deviation equals square root of 2, right? So this is going to be like 0, right? And we would expect getting zeros pretty much all around here, okay, until we get to somewhere around 10, 11, 12, okay, around here, okay? So at 10, so at the coordinate 10, 6, our y hat would be, at the coordinate 10, 6, it would be 10 plus 6 times 0, okay? And then so our y hat would be equal to 10, and we can say, all right, well, what's the probability of getting 12 if our mean is 10, okay? And so this is like finally a number that's not 0, right? Okay, and we do this, and we calculate this grid for every single pair of points, right? And then right now, because my only coordinate is 0, basically the vertical part is going to be the same for everybody. That's the likelihood. I'm going to combine the likelihood along with the prior distribution, okay? And so the prior distribution, when I get to 10, 6, okay, so here I'm at this location, 10, 6, right? So we have our, the prior probability asks, what is the probability that you get 10, 6 drawn from a multivariate normal with mean 0, 0. Right? So our original grid looked kind of like this, and we're asking what's the probability of getting this location, right? And so this is fairly low, okay? And so as I continue on and I do all of these grid points, then I would say, okay, so the likelihood for this column of points is going to be the same because our x term is 0, right? So the likelihood for all of these is going to be the same, but then the prior probability will get better and better as we get closer to the 0 right here. Okay, so the prior probability is basically saying, okay, well, what's the probability of getting this and this? And it's going to be the best right here, and then as we get further and further away, it's going to get lower and lower and lower. Does that kind of make sense? So we're asking, okay, so then, you know, we get to like right here at 10 comma 0, right? And you know, the likelihood says if we're using 10 comma 0, then our y hat would be equal to 10 plus 0 times 0. We're getting our y hat is 10, and our likelihood is what is the probability of getting 12 if our mean is 10 and our standard deviation is square root of 2, right? So we can calculate this. And then over here we ask, well, what's the probability in our prior distribution of getting 10 comma 0, okay? If our multivariate has a mean of 0, 0, well, the 10 is unlikely, but the 0 is most likely, so this is going to kind of be the highest, right? And so that's what I'm going to do in R. I'm going to just do a grid, okay? And the grid will go from -20 to 20. And from -6 to 6. And I'm creating a matrix called posterior, okay? And for every coordinate, I'm going to say W is the, you know, starting off at -26 or -6, and then we go across to, you know, 10 comma 0, and it covers all of these things. We're going to say, okay, make your W there. Then calculate what your y hat would be. That's going to be your mean. X times W is going to be your mean. And then the posterior distribution is going to be the product of your likelihood. So yeah, I'll get rid of this product term. It's not necessary. Okay. What's the likelihood of getting, in this case, 12, t is 12, if the mean is whatever is the mean predicted by this W with standard deviation S, and we multiply that by the prior probability of getting this exact coordinates of W. And that's going to be drawn from the multivariate normal. So we do this, and we calculate our entire plot as such. And so when we do that, the resulting, where'd it go? So we observe one data point, and then, okay, here we are. And so the resulting contour plot looks like this, okay? So basically, we've only observed one data point so far, and so it says, all right, this is kind of my best guess. Here is the perspective plot, and then I didn't do the OpenGL 3D perspective plot, but we could do that, sure. Okay. And so it looks like this, right? So we get this really skinny hill, okay? And this is what we have. Okay, and then, all right, let's try, okay, what would happen if I observe 3 data points, okay? It's the same kind of idea. We're going to do a grid approximation so we can consider basically all possible values of W, right? And then so, you know, we're just, let's say we're at some location. This is the location where W is going to say equal to 10 comma -1 or something like that, okay? Let's say this is what we have. And our first 3 data points is going to be, I'm going to just pull out x and t. So I've got basically 0, 1, and 2 for x, okay? So x is equal to 1, 1, 1, and 0, 1, and 2 for x. And then, so if I do x times w, my predictions, if x is 10 and negative 1, then my predictions for the mean are 10, 9, and 8. Okay, so my y-hats are going to be 10, 9, and 8. And then we look at what are the actual values that we get. Okay, and so the actual values t are 12, 11, and 11. So the actual values t are 12, 11, and 11. Okay, and so the likelihood is we ask, what is it all right if I just write it in kind of this notation? What is the likelihood of getting 12 if the mean is 10 and my standard deviation is the square root of 2, right? And then it's a product, so I have to multiply this by what's the likelihood of getting 11 if my mean is 10. I'm sorry, if my mean is 9 and my standard deviation is the square root of 2. And what's the probability of getting 11 if my mean is 8 and my standard deviation is the square root of 2? So this is going to be the likelihood. You basically plug this into the normal, each data point, right? Because it's the likelihood of your data given the current value of w. So with w, we get a vector of y-hats. I say, 10 minus 0 is 10, 10 minus 1 is 9, 10 minus 2 is 8. So that's what I get. This is my y-hats. So these are going to be forming my means. And I say, okay, what's the probability of these 3 data points? Does this make sense for the normal? I mean, for the likelihood of these 3 data points. And then the prior is just going to be, all right, what is the probability? So it's dmv norm. What's the probability of getting the coordinate 10, negative 1 from if the mean is 0, 0, and the so this is mu 0 and sigma 0 is equal to, 100, 0, 0, 5, okay? So the prior distribution is still kind of the thing that's centered at 0, and we say, okay, well, how likely is it to get 10, negative 1 out of there? And so we combine this, and we combine this. And we do the same thing for the entire grid of values across the entire plot, okay? Is that all right? So this is now just, so we are updating our beliefs about the distribution of W based on the likelihood of the data that we have seen. So then I create a grid here. Okay, and so that's all I'm doing. So inside my loop, my posterior is going to be the product. Here I'm going to have t is a vector of 3 values and mean is a vector of 3 values, and d norm knows to do element-wise normal calculations here. And so it's going to be the total product of those 3 values multiplied by the prior probability of dmv norm. Okay, and so we're going to do this for our entire grid. Okay, and okay. And so when we do that, this is kind of the entire plot, right? So we say, okay, now it's kind of all concentrated here because, and all of these other values, which give terrible estimates, basically have a probability of 0, okay? And so so I basically did the same thing, except I just changed the limits of my grid, and I said, okay, let's zoom in to 8 to 15 and something something, and then so if I change where I'm zooming into, this is kind of my new updated distribution for W0 and W1. Okay, so W0 and W1, the slope and the intercept, they're still random variables, but they are now coming from this distribution, okay? Where right now the most likely value is something around an intercept of 11.5 and a slope of something around negative 0.05 or something around there, or negative something. This is the most likely value right now, and we can kind of see these plots. These are the thing, and then we can do the 3D thing if we wanted to, okay? I can expand this and say, all right, let's incorporate 10 data points. It's the same thing, except now instead of 3, I've got the likelihood is going to be 10 data points, okay? And then so I do this, and when I do this, I had to zoom in to someplace different, and so now we're really getting, my intercept is certainly between 10 and 13, okay, with the most likely thing being around 11 point something, and the slope is very close to negative point something, okay? At this point, when I start to if I want to include more than 10 data points, it starts to break down because I run into underflow errors, right? So in floating point notation, we cannot represent numbers with an infinite number of decimal places. And the smallest value we can represent is on the order of, I don't know, 2 to the negative something. And so at this point, here I'm multiplying tiny little probabilities, and I'm going to multiply like 10 of them together or 100 or something like that. Those numbers get really, really, really close to 0, and our computer is not able to distinguish them between 0 and some other value. And so things get really wonky, and so the grid approximation starts to fail, okay? And so we are running out of time, so what we will do is, instead of grid approximation, we will actually do some math to kind of get at what the distribution should be, and that's where the conjugate prior comes in and plays nicely, okay? But what I wanted to illustrate was kind of the space for W, and when you're producing your posterior distribution, you're effectively considering every single possible combination of slope and intercept parameters and asking, what is the likelihood of my data under this set of parameters? What is the likelihood under this set of parameters? What is the likelihood under this set of parameters? And you're considering every single one of those possibilities to get your likelihood, and then you combine that with the prior probabilities of getting those combinations to get your posterior, or at least something that's proportional to your posterior. Okay, we'll end here for today. We'll see you guys on Friday. Happy Valentine's Day, everybody, and we'll see you then.